Namaskar, welcome back. So, this was the last slide where we stopped and we were talking about the significance of mapping quaternary deposits and how it can help us in identifying or delineating the different depositional environments. Coming to the geomorphic mapping part, the surface expressions has to be mapped, and if there are multiple events, that will also be preserved, and that we need to identify. So, there are different landforms in different tectonic settings that we will learn later in this course, and that will have in separate topics. Okay. We will have separate lectures for that. So, for example, in this mostly it has been shown for the reverse fault and the normal fault. What you will see where one block goes down and another block is stable. We can say this is an over here if we see. So, this is your foot valve and this will be your hanging wall, because this wall is moving down. Okay. Similarly, over here is the same in the normal fault, but here this will be your hanging wall, because this is moving up and this is your foot wall. Okay. And fault runs over here, surface expression of the fault with the warped surface. Okay. This one is your warped surface, or you can say folding is taking place over here, that can be easily differentiated. So, this is typical landforms which you see in normal faulting environment, that what we call the triangular facet. This part also we will learn when we are talking about the detailed landforms, but this is just an example which I am trying to show you here, that you will come across such landforms in the topography along the active faults. And third, this last one is your reverse as well as your strike slip component, where you will see a sort of an lateral as well as the normal, or you will have a reverse movement, which will result into different type of landforms like sag ponds, shutter ridges, offset of channels and all that, that what we have seen in one of the example of San Andreas fault system. So, if there is an channels which are flowing crossing this fault, for example, and if they are moving like this, okay, then this is what we call the offsets of channels. Okay. And here the movement of the fault will be something like this. Okay. So, this portion is moving this side and this portion is moving this side. So, this becomes a sort of an left lateral strike slip. So, this part, as I told, that we will be learning in detail when we are talking about the different environment. Okay. That is your faulting environments. Then if you are, as I told, that if you are having recurrent faultings, okay, then you will also be able to see the multiple sequence of deformation. Okay. Now, fault scarps basically are been demarcated. If you take up the geomorphic symbols, okay, then you will see this type of symbols are been used for different faults, type of faults in different environment, either it is reverse, normal or strike slip, then that can be demarcated with such symbols. But mostly what we are doing is that in preparing the maps and all that, okay, it is sometimes very difficult to put a very typical small features, okay, on map. But if you are having enlarged size of the map, you can have this type of information put in on that particular map. Okay. Otherwise, it is difficult. I will come to that. We have couple of maps how we have generated for Himalayas. We will talk about that. Now, after sedimentary, we have discussed about the sedimentary mapping, and then we talked about the that what sort of features in brief we have discussed, that what sort of features we will see in terms of the different faulting environment. Now, topographic mapping, after preparing the geomorphic map or tectonogeomorphic map, you need to conduct the field surveys. Okay. So, if we start from the beginning, what we were talking about is that you use the satellite data, you prepare geomorphic map, now you are heading into for the field surveys. Okay. So, topographic mapping is very much important. So, detailed geomorphic mapping includes preparation of the base map and profiles, topographic profiles of the landforms. Okay. Many landforms produced by paleo earthquakes are as small as, this is in terms of the height. Okay. It will be around 1 meter or up to 5 meters and all that. So, you should not miss out this type of landforms also. Okay. If you see a sort of an elevation change of 1 meter, then you just, because similar features or the change in the elevation can be related to erosion also, and even 30 meter high escarpment can be related to the erosion. But one has to be very careful in first delineating the faults and confirming that, okay, fine, this could be. Okay. Again, we cannot straight away say and arrive to the conclusion that this whatever we have mapped are the active faults. You need to conduct the field. Okay. But you can say the probable active fault trace, and you should not miss out this type of features. Even like as I told, that 30 meter, 40 meter, 50 meter high scarps could be related to erosion also. Okay. So, what we see, for example, if you are having like a topographic variation like this, okay, on surface, then this could be related to erosion. So, you need to understand that what is the dynamic around here, whether there is any river which is flowing across this, which could have eroded this portion, and this is the escarpment, or there is no river in this area, the rivers are flowing like this, okay, but there is an escarpment which runs here. Okay. So, this could be related to the fault. Okay. Because at all locations you may not come across to see this section. Okay. Sectional view will not be easy unless and until you are lucky enough to see this in wherever there is a river cutting. Okay. So, when one has to be very careful about this to differentiate about the paleo earthquakes and non signatures and normal processes, that is erosion and depositional processes related to the fluvial activities. Okay. So, typical contouring with interval of 3 to 15 meter is ideal to understand the overall geomorphic expression. So, this topographic mapping will help us in generating this type of contour maps. Okay. So, for example, this is from Northern Anatolian fault, where very detailed mapping was been done, which has been shown here on your right hand side, which shows the contouring or the map which was generated was of like the contours were of 0.2 meters, okay, 20 centimeter interval, and that helped them to identify this river offsets. Okay. Over here, if you see, then this is the offset of the river here, and then you have the offset over here also. Okay. And finally, they identified the trenching site. So, before getting into this like paleoseismic studies, you need to generate detailed. So, you need to have detailed map. Okay. For that, you need to have the what we call as the topographic mapping of the landforms. Further, this is another example from US, where the quaternary landforms which were been displaced by the fault. Okay. So, fault runs here. So, this displaced landforms were been identified on satellite photos. Later on detailed mapping was been done, that how much offset is been seen in different landform of different ages. Okay. And that also helps you in identifying the slip rate along the fault. So, for this high resolution mapping can be done, but as I have been mentioning from the beginning that this methods now we have redundant already, we have come down to UAV mappings and all that. Okay. Now, generation of maps, okay. If we talk about, then this is from what we have been doing in Himalayas, and particularly the Kumaon Garhwal Himalaya and then Punjab Himachal Himalayas, what we have done. So, we have generated very high resolution maps, and this is everything is been put on the GIS platform, where it includes the different level of terraces and alluvial fans. Okay. So, we can say that we have included in this map all geomorphic features and active faults. Okay. And then since the aim of this exercise was to put all information on a digital platform, we generated this complete map on GIS platform. So, active fault signatures were identified based on surface morphology using high resolution Cartosat stereo photographs on ArcGIS. Apart from the faults, different level of terraces, fluvial landforms, deformational features along with lithology and drainage have been marked in this. Okay. Now, the map which we generated can be extracted at different scale. Okay. And this can be 1 is to 25,000 or 1 is to 50,000 or 1 is to 1 lakh, depending on the area covered. Okay. The whole map we divided into 25K scale, and indexing was been done. So, this is a pretty good exercise which we did. Okay. Still we are working on this to refine the cataloging of this maps and all that, but yes, the red lines what you see here is all active faults which are been marked. Okay. And the idea behind this is that in coming months we will put this on digital platform, or maybe in a year's time, and this will be available to the public. Okay. So, if you click any point here, for example, this area, then it will give you the complete history of if it is available in terms of the paleoseismology. But let me tell you here that most of the studies, paleoseismic studies which have been done are along the Himalayan frontal thrust only, okay. But very few on the hinterland side, that is the faults which are away from the Shivaliks, or maybe we can say sub Himalayas. But if you click on this, then you will be able to generate the map, and that can be used for any purpose. Okay. For urban planning, for having putting any lifeline structures. So, avoid putting the lifeline structures on such fault lines. Okay. So, what was been done is that this whole map is divided equally in smaller grids. We can see the grids here. Okay. These are the grids here, smaller grids, and more than 40 maps are generated along assigned area. This is way back. Okay. But we have generated more. Okay. And active faults are identified based on the variation in the surface morphology and displaced or deformed alluvial fan surfaces, fluvial terraces, river offsets, tilted surfaces using high resolution Cartosat data. Okay. Different level of fluvial terraces and drainage have been marked. Okay. The map are generated at different scale, that what we have discussed in the previous slide also. Okay. Now, this is how the coding was been done of this map, and this map is basically of this part here. This is the area which I am showing in the next slide. Okay. So, this is the area which we show here, and now we can see that there are number of this points which talks about the number of that particular grid. Okay. And that how it has been indexed. Okay. So, most of the areas have been indexed. So, if you go in further detail, this is from the Dehradun foothill zones we see, okay, and that what you have, okay, the further maps from this area. Okay. So, we also try to take care of that the illustrations which have been presented, okay, that how easily we will be able to differentiate and put that information on map, so that it is visible and readable to the readers or the users. Okay. So, initially we did with different color codings we used, okay, of the same color and different variation of that shades of that same color, but later on we realized that that is not giving us a complete a demarcation or the contrast between the different landforms. Okay. Then we use different coding. So, if you see on the left hand side, we have the shades of same yellow color, but on the right hand side, for example, if you look at this portion here, okay, and then this portion over here. So, what usually the issue came was that we were unable to differentiate on the paper print or so the color variations which we were doing of different shades of yellow, and we were able to it was difficult to differentiate between the landforms older and younger. Okay. We were not able to do that. So, then we use different color codes, and that is again a huge sort of an time taking exercise, but this has to be done. Okay. This has to be done for any maps which we are generating in terms of the active faults. Okay. So, the right hand side map, that was we finally adopted the color codes, and that how you can differentiate easily now the different landforms as well as the lithology. Okay. So, what is that? Okay. So, the first one is from the Haldwani area, and another is Ramnagar area in the Kumaon Himalayas. So, where you can differentiate easily different terraces as well as the alluvial fan surfaces. Okay. Now, coming to this part again, as we have discussed. So, this is what type of maps you will be able to generate. So, this is the portion here. So, if you are having complete big map and then you want just that map, you just put the box there, and then that will generate your detailed map. Okay. And this includes everything, all landforms as well as the faults. Okay. Now, one part which I discussed in the previous lecture about your symbols. Okay. Now, sometime it is bit difficult to like give an information to the reader that what type of fault is there. Okay. However, even in this map, we are facing issues with the putting symbols and all that, because there are again limitations of the software and all that. So, one part is that if you have a thrust fault, then usually the most commonly used symbol is this type of, like you have high line and then you have a rectangle here, and this rectangle is particularly showing you the dip of the fault also. Okay, in which direction it is dipping. Okay. So, this is for the reverse fault, which we tried here, but if you see carefully, then our rectangles are running here and there. Okay. So, that we need to fix. The other part, in most of the maps, which is so this shows that the fault is dipping in this direction. Okay. Now, in most of the maps which are not only generated in India, but other countries also, what they use is this type of comps, okay. And this simply show that this is fault here, fault line, okay. And this portion which is towards the comp is the down thrown area. So, this means this is down and this side is up, okay. So, that is more than enough for us to differentiate that, and I didn't say that, okay, fine, this side is up, this is down, okay, on map scale, okay. So, that what we did, we followed even in Japan, even in US, in most of the countries, this is the simplest way of presenting the active fault topography, okay. So, if you look at this portion only, then the comps which have been shown here, this is what you have, the fault scarp, okay. Now, this fault scarp here, if you take this, then this area is down, this is up, this is down, okay, with respect to this one, but here with respect to this fault, okay. So, this is what is been marked as an HF1, okay. Then you have HF2, and this is BT is the back thrust actually. So, with respect to this fault, that is BT, this area is down, this is up, okay. But with respect to HF2, this is down, this is up, okay. And then similarly, for with respect to HF1, this portion is up, this is down, okay. So, this type of topography you will have to look at very carefully on satellite data and then do the field mapping. If I take a cross section here, okay, I will discuss this later also, okay, because this is the area where we have done very detailed mapping, okay. So, if you take the cross section in this area, for example, A and B, then how it looks like, okay. It is something, it goes like this, okay. So, it is a flat area here, then this goes up, then a flat area, and then this goes up, and then it goes down like this, okay. So, this is your back thrust, this is your HF2, and this is your HF1 scarp. So, you have A and B here. So, this is how we do, okay. Of course, we have the information that there is a fault transfer here in the section, okay. So, this is the fault geometry where this portion moves up, this portion moves up, and this portion moves up, okay. And this portion, what we see, this part is Indo-Gangetic plane, that is your, this one is Indo-Gangetic plane here, and this portion is your HFT, Himalayan frontal thrust. So, further as we have been talking about that these maps have been catalogued with unique number, and what we did was we used this two corners, okay, to name this sheet, or we can say the map, okay. So, here if you see, this is what we have is the D4 and H8, okay. So, these corners have been taken, but still we are trying to like refine this, and probably will be numbering this with the sheet numbers, okay. And as I told that we can easily click on it and you will get the maps, okay. So, that is our main aim, okay. Now, fault scarp profiles are important, as we have been talking about in last lectures we have also discussed, okay. So, initially this is what we call the ancient technique, Paleolithic style of mapping, okay. So, initially we used to have the ebony level, and then we used to ask somebody to hold the post and post us all with the measurement and all that, okay, or the stick, okay. And then we try to focus on that and then say okay fine, this is matching. So, this is the height of that with relative height, okay, and that what has been shown here in this photograph. Okay. And it is important if like fault scarps will be seen something like this, okay, then you need to have the mapping of the down faulted block, or we can say the down thrown area and the up thrown area, okay, and that will help you in generating the profile, because we need to have the height of the scarp also when we are calculating the slip, when we are talking about that how many events were responsible, that those events are paleo earthquakes or ancient earthquakes, how many earthquakes were responsible in producing the scarp. Okay. Because whenever there is an, for example, one earthquake, then second earthquake, third earthquake, so elevation will change, and this elevation change is seen on the surface, has to be mapped, okay, and that is how we usually cross our topographic mapping from the base, and that is the unfaulted or undeformed region to the deformed region and further up. Okay. We will stop here and we will continue in the next lecture talking more on the field observation and field mapping. Thank you so much. Namaskar.